Yeah, I'll share my screen. I can't share screens. It's disabled.
Yeah, I've enabled it now.
All right. You can see my screen.
Yes.
All
Let me
right.
set the names. Give me a second. All right, go ahead and begin, guys.
All right. So our first off, my name's Andrew. With Vito and Tyler, and our topic was how to decrypt SSL or TLS with Wireshark. So first, we're gonna cover, a lot of us have dealt with Wireshark if we were in Taehoon's class. If you don't know what Wireshark is, it's an application that basically it's a network protocol that analyzes the data packets that pass through it. It intercepts the data packets that are being transmitted over a connection, whether it's wired or wireless. And many of the data packets are encrypted. They're encrypted through two different ways. The secure socket layer, also known as SSL, or the transport layer security, also known as TLS. And the reason for that is to keep, the user safe because you don't want your data going from one another and it being intercepted by the wrong person. So the process in which this works is in order to decrypt it using Wireshark, decrypt TLS using Wireshark, we're going to use a pre-mastered secret key. And a pre-mastered secret key is generated by the user and it's used by the server to decrypt the session traffic. There's 4 steps to doing this. The first step, you have to set the variable, the environment variable. And then after we set an environment variable, we're going to launch a browser. I believe we're going to be using the PNW website. After that, we're going to use launch Wireshark, and then we're going to start capturing the, the packets from PNW to our computer. And we're going to decrypt the session keys. First step, like I said, we're gonna create the log file that contains the pre-mastered secret key. The process is pretty simple. We're gonna demonstrate that, so I'm not gonna read this out loud. It'll just be shown. The next step is we don't want to launch Wireshark first. We want to confirm that the log file is being used. Then we'll launch Wireshark, and then we're gonna visit the website Purdue or pnw.edu. And the logs from us visiting that website are going to go into a file called SSL keylog file. And then from there, we're going to configure Wireshark and use the keys. Following that, we're going to edit our preferences. And then we're going to copy our pre-mastered secret key that is generated. And we're going to paste it. And then we're going to be able to view the different data. And then following that, we're gonna look at the packets and go more into depth with them, and I'll have Vito and Tyler demonstrate that now. Let me stop sharing.
All right, so the first step is to go to File Explorer and find. Once you go to File Explorer, you need to right-click this PC and click on Properties. You need to go into Advanced System Settings, which is where he's clicking on right now. And for further, the button, the environmental variables button, you need to click on that. Then after that, go to the new user under variable. You click on you type in the variable name, which is SS key log file. And then the location, and then you need to select a specific location for it, which is
It could be any location. We're just
yeah,
gonna desktop.
uh, after that you close all the windows. After pressing OK. Then you open up the log file in Notepad. moving on, like you got moving. Next time you need to go on Wireshark, open that up. You need to select Edit. Click on the Edit button and find Preferences. And you need to go to the Products button or Protocols button. Sorry. Scroll down and go to the bottom and find a TLS because that's the protocol we'll be using. Should be scroll up a little bit. There it is. Once you do, you press OK. And then once you press OK, you start like a Wireshark capture by double clicking on the Wi-Fi here. Then after that, we go to open our browser and we go to P&W's website. All right. After that, then we go back to Wireshark. Select, and then you stop the capture. Once you stop the capture, you need to like filter it out to make easier, which we will do by typing SSL. And then we scroll through until we find a specific like protocol, which is HTTP 1.2. And once we go to do that specific protocol, we need to find something along. We need to find like location which is along the lines of either text/CSS or text/JavaScript. They're basically more or less kind of same thing, except CSS shows the website.
You passed one, Vito. Yeah, there's one there and there's one up. Yeah.
Except the difference that shows kind of like the coding of the website more or less in CSS or in Java, depending on which is which.
This is just providing us with the source code from the website as
Basically.
well. Yeah.
That's more or less the gist of it. You're going to keep on scrolling through and finding, CSS or JavaScript or plain text, and it's going to allow you to view the plain text of the website or the JavaScript or CSS code for the website.
And that's how to decrypt SSL or TLS. They're both similar using Wireshark.
All right, so I understand what you do is you're basically decrypting you have the key to the browser, right? That's sort of the idea.
Correct. That was the pre-mastered key that was generated.
Yeah. So you have how the browser would encrypt. You have that key, and therefore, as you're going through the traffic, you can decrypt the traffic.
Correct. Yeah, I don't know if you noticed when Vito was demonstrating when we went to the protocols and we selected TLS. It looks like we actually forgot to mention. Vito, if you want to go back to that so I can show what we were exactly talking about. If you want to share your screen again. Yeah, when we were in Wireshark and you hit edit and preferences. Yeah, so when you go to the protocols and then in TLS, if you scroll back down, you notice at the bottom the pre-master secret key log file name is the directory that we created for the environment at the start. And that's what's being used here.
So this would be used, by a system administrator possibly to kind of keep track of all traffic.
Right.
All right. Are there any questions for this group? No questions? All right, great job. Thank you, guys. All right, so
thank you.
Yep. Let's move on to the next group.
Alex Harris, Cody Snark, and Anthony and Jamka. We did our presentations last week, but we had a small technical issue.
Okay.
Can we demonstrate that real quick from our last week? Awesome.
Yes. Let me get your names.
Sure.
Okay, so yeah, Anthony, Alec, and Cody, correct?
Correct. So
Steganography.
do you want us to re-present, or do you want us just to read?
No, just do the demo. That's okay.
For sure. Gotcha. All right. I'll be streaming first. So on my screen, you can currently see that I have my terminal open up for Steghide because we are using Steghide for Steganography. So I have ran it through previously, where I enter the passphrase being happydog123, as well as using RSA to create a cipher of the password that I will pass on over to Cody, which will just be my cipher and the image. I'm going to pass the sharing over to Cody.
Okay. All right, so I'm gonna just download his cipher. And this is where we messed up last time. You have to open original in Discord, fun fact. So I'm just gonna open here and I'm gonna save it.
Discord has a way of compressing it, so it was compressing the actual password, so it wasn't able to be registered properly.
Yeah. All right, so I'm gonna move this into here. Run the decryption so I get his password. And then the command to extract the information you put in there is this. Put the picture, type his password, and it's going to open, or it's going to copy what he put in here, which was this. And now I know this was his message. That's pretty much it. So yeah, the only part we messed up on last time, it wasn't like to do with the Steghide part, it was Discord. Like I didn't open this right. And so it was like a compressed version, and so I couldn't find what he hid in the actual image.
So what's the second file for? I get that you get the image, you use the program to remove the steganography
You're talking about this
embedding.
cipher, or this one?
You get a value, right? You get a file, but then what was the other file?
Oh, that was a cipher. So the way, what is it?
But it wasn't hidden in the image.
No,
So that I guess
he sent it to me
that's what it's
directly.
called.
He sent it to me directly, and it was an encrypted.
Right, you sent a cipher, right? An encrypted file.
Correct.
And then what's in, so if that's the secret file encrypted, what's in the
This is
steganography?
an encrypted version of the symmetric key used to encrypt the data in the steganography file. Because it uses AES 128-bit to encrypt it.
Happy dog 123, that password was in the encrypted file.
Yeah.
You decrypted it, got that password, and then you entered that in
When I extracted it, yes.
Steghide,
Yeah.
and then you get the encrypted message.
Yes, correct.
Oh, okay. So it's basically that you just hid the password, but you could have just known the password.
Yeah, like if I just told him the
Correct.
password, we could just use the same password for a lot of.
A lot of
I
people,
wasn't getting that, but
Yeah.
I get it now.
when a lot of people like through social media means like Twitter, stuff like that, they'll hide certain imagery, so you know what to be using for that. When I was doing the presentation last week, a lot of pedophiles will use pizza as a way to kind of say, this is a hidden file within here. And so it's a way to actually direct people to specific means of different websites or like a dark web website of we're using like the Onion browser.
Okay, all right. I understand. All right, great job. Great job.
Thank you.
So that was your demo. Do you guys have any questions for this group of Cody, Alec, or Anthony? No questions? All right, great. Thank you very much. Great job. All right,
Thank
so
you.
now who do we have left?
Jason White and Ryan Frederick.
So,
I think somebody else tried to talk at the same time as me as well, so there's probably another group.
okay, who else?
And Ahmed and Zachary.
Okay, so you guys are left as well, okay?
And then also Eric Roddy and John Sorensen.
Okay, so 3 groups left. Anyone else? Right, that's good to know. So the first group that spoke, set up, please.
Alrighty. I'm gonna share my screen now. Can you see my screen?
Yes, let me just get the names.
For sure. Good to go.
So Ryan and Jason, just two.
Yeah, just Jason and Ryan. Yep.
Okay, Steganography. Wow, you
Yep,
guys
more steganography.
really like that topic. Go ahead.
Alrighty. So we also did our project on steganography. So to start off our presentation, it's just going to be a definition of modern steganography. So steganography is the practice of concealing some data within a file so that it would appear harmless. Example, a secret message hidden within an image, video, or sound file, as you saw in the last presentation. So the purpose of steganography is to hide a secret message while also attracting as little attention to the ciphertext as possible. It is maybe useful in places where encryption is illegal or restricted, such as China. So we also did our project on Steghide. So Steghide is a program that allows you to embed some secret message with an image or an audio file. It is available on either Windows or Linux. Some of the advantages of Steghide is it provides confidentiality by using AES. It also provides integrity by generating a CRC32 checksum, and it cannot be detected by first-order statistics. Some disadvantages of Steghide, though, is that Steghide or a similar program must be available in order to decrypt the message on the receiving end. And so this next slide here is kind of just talking about how Steghide works. So I'm just going to go over the text first, and then I'll explain the image. So the first secret message is compressed and encrypted. Next, the algorithm constructs a graph using a random sequence of positions of pixels in the original image file. Pixels that need to be modified are represented as the vertices, as you see right here in the picture. And the pixels whose values are similar to the values needed by other pixels are represented by the edges, which is what it's connecting these vertices here. So pixels with the correct values needed to embed the secret file by chance are sorted out, which is kind of like, which is kind of like this little guy right here that's not connected to by any of the edges. So the algorithm then calculates the best way to sort the graph so that each vertex has the maximum amount of edges possible. The secret message is then embedded by exchanging those values given by the matched edges. Lastly, a CRC32 checksum is calculated. And as mentioned before, audio files and text files can be hidden. So when using audio files, the algorithm is the same, but audio samples are used rather than the pixels. By exchanging pixel values rather than overwriting each pixel, this algorithm is resistant to first-order statistical tags, such as the amount of times a specific color appears in an image. And then on this last slide here, it's just showing you how if you were wanting to embed the image, this is what you would use. If you're wanting to extract data from the file, this is what you would use. And then if you were to, the command Steghide enc info will show you every algorithm supported by Steghide, which is what this picture is right here. And so now I'm going to pass it on to Ryan, who's going to give a live demo.
All right. So how we implemented Steghide is we created a Python program, and basically this just makes the, it plugs in all of the syntax and just basically makes the program more user-friendly. It just asks simple questions like, what's the name of the file, where's the location, and do you want to use the default encryption algorithm? And then I made this executable from any directory by placing it in user/bin. And then if I just run this program, I can embed a file, and the secret message is secret.txt. The image file is purdue.jpg. The name of the steg file will be steg.jpg. And then if you want to use a different encryption algorithm, the default is AES. You can press N, or N, and then this will list all of the available algorithms. But we're just going to use this one, which is, that's just AES 128. So we'll paste that in there. and then give it a password. And then here's the original image file. And then here is the one with the embedded data. So as you can see, there is virtually no difference that you can distinguish. And then if we go back to that program, we can choose extract and then enter the location to the steg file and then put a name for the plain text file. And then just put in the password. And then here is the original text file. And here is the file that it extracted. So as you can see, they are the same. But if you wanted to verify the integrity, you could put in SHA-1 sum and then the original text file, and then do the same for the extracted text file. And there you can see that these two are the same. One way that you could tell if you might want to know if the file has embedded data in it, first, the easiest way is if you have both the original file and the suspect file. And then the easiest way is to check the file sizes. In our case, our file with embedded data is actually smaller than the original because Steghide compresses the data before it embeds it. And then if you can't tell from there, you could check the two hash values as I did, but with the two images. And if those are different, then that means that the two images are different. And another method is using this website that I found here. What this does is it allows you to plug in two images. For example, let's do the original image. And then let's do the image that we created or embedded the data into. And then what this does is it allows you to highlight the differences in each pixel. It'll compare the two files pixel by pixel, and then this will highlight the differences in each of the images. So as you can see here, all of that red is where the data most likely is embedded in. And those are all of the different pixels between the two images. And I think that's about all for our topic. If you have any questions.
Excellent job. It's actually very interesting how that works. Yeah, very good. Sounds like a research topic almost.
Oh, definitely.
Create an algorithm, train it with a whole bunch of images that have been already embedded with secrets, figure out the pattern, and then filter out the, like what you did. So it's very good. Very good job.
Thank you.
Any questions for this group, guys? Any questions for them? No questions? All right, excellent job. Okay, so we got two groups left, I think. Who would like to go next?
Me and Ahmed could go next.
Yeah.
All right, so just give me a sec to write your names down.
Yep.
Okay.
All right, go ahead, please.
Hello, everyone. My name is Ahmed, and our project is OpenStego. So steganography is the art and science of hiding information by embedding message within a cover media, which is seemingly harmless. It works by replacing bits of useless or unused data in a regular computer file, such as graphics, sound, text, HTML, or even a floppy disk. So there are 4 types of steganography: text, audio, video, and image steganography. So image steganography refers to hiding information such as audio file and another image. In our project, we will use the process of hiding text into an image file. So here LSB is known as least significant bit with the lowest bit in the series of numbers in binary. It is either the leftmost or the rightmost bit in binary number, depending on the computer's architecture. It hides the message so that nobody is aware of its existence. Most commonly used to hide text and or an image within a cover image. It also operates on a principle that the human eye cannot distinguish between 2 shades separated by only 1 bit. So one of the most important advantage of LSB is its simplicity. It allows high perpetual transparency, and the data hiding capacity of LSB technique is high and more secure. So the output feedback is a mode of operation for Cipher. It is the encryption mode that AES use for in our project. It has some similarity to the Cipher text feedback. It permits encryption of a different block size. It makes block cipher into a synchronized stream. Generates keys blocks. It also it is a method used in our program OpenStag.
All right, next I'm going to go over some of the code before I actually do the demo, just to explain a couple things. So the first part of our program is to simulate how you would go about cracking the AES password used in the encryption process. So I tried to make this pretty simple to understand. So I did a quick array with a couple passwords and then 1 stored password. And in real life, you would be using hash during this, and you would be checking the hash of the known password with hash like a dictionary file. And this function pretty much just checks each item in the array against the original password to see which one, and then it stores that for later in the program. Then next, I did a Linux command in Python, and this is the CMP command, and this is pretty much a text representation of the different pixel values, similar to the last group where it had the red values were the different ones. This is just a shell command to do the same thing. And this is going to compare the bytes of the cover image, which is the unencrypted version, and the encrypted version after. And it's going to write out which ones of those are different so you could go and see. Then this was an attempt to try to figure out how to basically crack the encrypted image without using the original program. And it was pretty ill-fated because there was a lot of different bits for most of the time, and the OpenStegon program is a little different from the other ones in that it hides dummy bits that aren't used for the encryption message to try to throw you off if you were to try and crack it this way. But how you would go about cracking it is you would look at the different bytes and the pixels, and you could tell, for example, if one value was 65 and one value was 66 in the other image, you'd be able to tell that they added a 1 onto the end of the 65 to hide the image data in, or message data. But I couldn't figure out a way to do this in Python, so I figured I'd just explain that a little bit. And then you'd go about the same way to decrypt it after you had all those in order as you would a regular file. But the only other issue is OpenStego uses the OFB mode of encryption, which is similar to CFB, but OFB uses the IV every single round instead of using the ciphertext. And I couldn't figure out how to get the IV from the original program, so that didn't really work that good. But I just made it like a little demonstration, and this is how you would do it if you had those values. So now I'm going to show you guys how the program works. Okay, so now I'm in the virtual machine, and this is what OpenStego looks like. It's just a simple Java program. And then you just input these values. So you first pick the message file that you want to use, and that's in this folder. This message right now just says, hello, my name is Zachary. This is a test, but we won't get to really see that. And then you pick a cover image to use. I just picked a random Starbucks image off the internet because that's where I was when I wrote this. And then you pick, you name the file that you want it to output to. Oh, can you guys not see my virtual machine right now?
We are seeing slides. I think this is slides.
Okay, hang on.
Yeah.
Let me just stop it and share. Okay, how about now?
Yes, this looks like a virtual machine.
Okay, so I'll just run back through that. So basically, I just picked a message file, and like I said, it just says, hello, my name is Zachary. This is a test. Then I picked, you can use any image you want. I just picked a Starbucks image off the internet. And then you enter what you want to save the image as. I'm just going to save it as that. Then you click OK. And then you can enter the password. So this password, the AES encryption doesn't encrypt the password in this program. It actually encrypts the bits or bytes of data that are used for the message. You can use any password you want here. And then you just click on hide. And then you get this message once it's a success. So once you did that, I don't need the OpenStego anymore or this. And then I'm going to show you how the Python program runs. So I'm just run it real quick. So you can see the password got cracked off of the first bit of code that I explained. And it is just a simple explanation of how you'd go about cracking the password. Then you can see that the files were compared, and I'll show you the output of that in a minute. And then the picture was decrypted in quotes because it wasn't actually decrypted, but it was just a simulation of how it would be decrypted. So let me show you the different bits, and then I'll explain that a little bit. Okay, so this file is the difference in bits from running the compare command in Linux from the original image, unencrypted image, and then the encrypted image. So this first row of values is the pixel location. So as you can see, there's quite a bit, almost 2 million. And then the second row is the pixel value for the cover image, and the third row is the pixel value for the encrypted image. So what you'd need to do in the next step of cracking this would be go through all of these and see, like, for example, this one on the bottom is 65 in the original image and 64 in the encrypted one. So you could tell that this is now storing a 0 instead of the 1 that would end in a 65 in binary. So you'd have to go through and pull out each one of those 0s and 1s for all of the values that are in this compare command, which there are quite a bit. And then you'd be able to run the AES decrypt on those using the password and the IV, which I wasn't able to get. And then once you did that, you'd be able to see what the original message was in there, but that was pretty difficult. So I figured I'd just explain how it worked, and hopefully you guys learned a little bit more now about steganography. This might have cleared up some of the questions before, but if you have any more, feel free to ask now.
Nice. I liked it. I like it. I like research. All right. So are there any questions for this group, guys? Any questions? So it seems like from both groups, what we've seen is that the images, you have to have the original image, right? And then, so when you do the steganography, don't grab images that are well known. That seems you have to grab an image that is unique and that no one has the original. So good, good. All right. Are there any other questions? Okay, no questions. All right, great job. Thank you very much. All right. I think we have then just one more group, correct?
Yes, I believe so.
Okay, so again,
It's
names on the and on the screen, and then you can begin when you're ready.
okay. So it will be me, Jonathan Sorensen, and Eric Karate. We decided to do our project on AES counter mode and basically programming it to implement it. So first I'm going to go into what counter mode really is. Basically, counter mode turns a block cipher into a stream cipher similar to OFB. It is slightly different in the fact that each block is individually encrypted and decrypted. I'll show that a little bit later in the later slide. It generates the key stream block encrypting sequential values of the counter value. So basically it takes a nonce or nonce and it adds a counter value to each individual block to basically add randomization into the encryption algorithm. So that way when each block, if the blocks have similar values underlying, like in the plain text, it's not immediately able to be decrypted. And then the counter can be any function that produces a sequence which is guaranteed not to repeat for a long time. But typically the counter is just added by one in standard practice. So some advantages to using counter mode is it allows random access of basically each individual block during decryption, because again, it's not using any values from the previous block to encrypt or decrypt. Counter mode is well designed to work on a multiprocessor system in the same context. Basically, it doesn't use the blocks are individually encrypted and decrypted, so it can decrypt or encrypt multiple blocks simultaneously. And then each block being encrypted and decrypted separately means that it is possible to jump from one point of a video, for instance, or audio or anything like that, into another point without having to buffer the full video prior to the specified point. Some disadvantages to CTR is that it can only use a nonce once with each key. Since each nonce is limited in length, this means that a key can only be used so many times before it would be considered insecure, as you would be able to possibly trace back the data and basically break some of the encryption. So this is the general layout for how the encryption works. You take the nonce at the top, you add the counter to the nonce, and then the nonce and the key get combined and then get XORed with the plain text, and then you get the ciphertext. And it does this for each individual block of whatever you're encrypting. And then for the decryption, it's essentially the same. The only difference is that you're taking in the ciphertext and XORing it and getting the plain text. So this is our general Python code. We're also going to be showing the demonstration directly after this. But basically, we generate the keys here. So we're creating a key and the nonce value. And then we're also writing our plain text to a file. So just to make it easier to mess with. And then we're encrypting the data using this method here, and then decrypting the data here, and then executing the functions at the end. And then this is how it looks when it's actually executed. And then I'm gonna hand it off to Eric to show off the actual execution.
Okay. You guys can see the screen all right, right?
Yep.
Okay, so this is the Python code John just showed. So here, I'll start by running it. So you need a plain text file. This is the message we have written in it already. And then I'll run the file. And then you can see it generates the key, the nonce, and it encrypts the plain text and the ciphertext. For demonstration purposes, it also prints out the ciphertext and the plain text here. So in the program, to encrypt, basically we create our counter by first randomly generating the nonce, which is 16 bytes, and then basing the counter off of that. And then after we create the cipher object and pass the counter and the key, it's then XORed with the plain text to produce the ciphertext. And the process is basically reversed with the decryption function. Yeah, that's it.
Any questions?
All right, great job. Can you go back to that graph, the little graph that you had?
Yeah, I'll pull it up in just a second.
Your code is also great. We'll come back to it, but yeah, if you can just bring that up. You had a little graph. All right, this one, yes. So this is very interesting, right? So in the class, we talked about how ECB was insecure, right?
Yeah.
This is ECB, except that you guys have that nonce, correct?
Yeah, basically it's a slightly more sophisticated version of ECB.
So the nonce is like it's the IV, the initialization vectors, but now they don't have to be the initialization vector from the previous step, correct?
Yes, correct.
So this nonce, the question that I have for you is, how is it generated? Is that what's pseudo-random sequence?
Yeah, the nonce is pseudo-randomly generated.
So it's a stream cipher, basically, based on that initial little key that you have, the seed, and then you're generating it to be of the length, I assume, probably of the block, but it's a stream cipher.
Right, that's what John pointed out.
Yeah, so that's how, okay, that's how you get a block. Each block becomes the IV, basically. And that way they're no longer ECB, because even though they can be treated in parallel, as you guys mentioned.
Yeah.
Very good. Can you go back to the code? That last code?
Yeah, let me stop sharing my screen so that way Eric can show his.
All right, so basically here then, you have a text file where you're keeping a key, basically, and then the counter function is gonna be what generates the stream, I assume.
This just initializes the counter right here, and then
And then the counter is used in AES.
right.
But, so the counter, something here generates the stream, right? And I assume it's associated with the counter. Now counter from crypto utility import counter. Okay.
Yeah.
Right. So that what do you guys know what that does exactly? I mean, I understand the idea, but
I haven't done too much digging into that.
yeah, I would almost say that this is the algorithm that generates the pseudo-random sequence. Kind of keep it separate from AES, which should only be the AES block cipher encryption. But I get it. I think I understand how it works. Okay. Do you guys have any questions? Rest of the class, any questions? It's very good. It's a great job.
Thank you.
Any questions? So some very interesting things, right? So hopefully watch these videos again, because there might be some questions. These guys, just made your lives harder on the final. All right. Good job. All right. Great job. Thank you very much, guys. All right. So I believe